Welcome back. This is the third video in the playlist that deals with equilibrium calculations, and is part of the playlist that deals with chemical equilibrium. In each of these videos, what I want to do is extend each example into a somewhat different realm. So after the series is done, the series will represent a variety of different kinds of calculations. So let's get started on this one. So in this example, what we're doing is we're combining 2 molar hydrogen gas with 2 molar fluorine gas in an initial situation. We're allowing the reaction to come to equilibrium. The Kc is 100, and I'm going to rewrite it next to the equation. The Kc is respectively large, and that means that the delta G for this reaction is going to be negative. And the only reason I bring that up is because there's going to be an appreciable shift to the right. Now, in terms of the amount of HF that's produced. Now, what we're going to do first is set up our ICE table, and the only reason I keep bringing that up is because the industry tends to use that term quite a bit. With my students, I call it the box. And essentially what we do is we record our initial information and our information regarding the reaction after equilibrium occurs. So what I do in my box is I write down the conditions that we have existing before equilibrium is reached. We have 2 molar H2 and 2 molar F2. So we have equal initial concentrations of both of the reactants, and we have 0 of the HF because we assume in the before situation that no reaction has taken place at this point. Now, once the reaction comes to equilibrium, there's going to be a shift to the right. We know there has to be a shift to the right because we're starting the reaction out where there is no HF. So the only direction that the reaction can move is to the right. So there's going to be a shift to the right to produce some HF, and that means that we have to pay attention to the stoichiometry of the reaction, noting that there's 1 mole of H2 that must react with 1 mole of F2 to produce 2 moles of HF. So the H2 is going to decrease by x, by 1x, and the F2 is also going to decrease by 1x, and the HF though is going to be produced at a rate of 2x. So now we have our table set up. We can go ahead and write our equilibrium expression. So I always start off by writing the expression with no numbers. So Kc is going to be equal to the concentration. We're in molarity here, so we're not dealing with partial pressures. So we have Kc. We use square brackets to indicate the molarity, and it'll be a square bracket HF raised to the second power based on the coefficient, law of mass action. All right, and this will be divided by concentration of H2 raised to the first power times concentration of F2 raised to the first power. Now I'm going to plug in my numbers. So we're going to have 100 is equal to 2x quantity squared over 2 molar minus x times 2 molar minus x. All right, now if you've been following my playlist, then you would be aware that the previous example looks similar to this, and you probably are saying to yourself, oh my god, here we go with the quadratic equation again. But like I said, each of my videos is designed to show you a different situation. So let's simplify this a little bit further, and to emphasize that, I'm going to change my color. So we're going to have 100 is equal to all right, let's deal with the numerator. It's going to be 4x squared. And then on the bottom here, this can be rewritten the following way. 2 molar minus x in the parentheses and then the whole quantity is squared, because it's this quantity times this quantity. Now notice the trick that we can use here, because we essentially have a perfect square. We can come in and take the square root of both sides. Okay, and when we do that, we're going to get 10 on the left, and then this is going to be equal to 2x on the right and over 2 molar minus x in the denominator. So now we have a problem that's considerably easier to solve, and we're not going to need the quadratic equation. So you want to pay attention to these kinds of problems. Don't just jump into having to use that horrible complicated equation. All right, so now we can go ahead and solve this. So it's going to be 10 times 2 molar minus x is equal to 2x. All right, and moving on, I think I'll go ahead and change the color. We're going to have 20 minus 10x is equal to 2x, where 20 is equal to 12x, where x is equal to 1.67. All right, now we can go ahead and solve for the concentrations of the various species. So for the H2, which is the same as the F2, so I'm going to put these two together, we're going to have 2 molar minus 1.67, which is equal to 0.333 molar. And for the HF, the concentration is going to equal 2 times 1.67, or 3.34 molar. All right, notice that the concentration of and what I'm going to do now is take you through sort of the common sense of checking answers. But it starts with this. Recognize your equilibrium constant is a large value. So the concentration of HF should be large by comparison to the concentration of the reactants that you started with. And it is. There is a proportionality difference here, which is on the correct side based on what your equilibrium constant looks like. And then what we can do is go ahead and plug these concentrations into the equilibrium expression to see what we get, and then make a comparison back to the known K values. So this is going to be 3.34 squared over 0.333, also squared because it's F2 times H2. And what we get out is 100.6. So there's a good correlation between the value that we get based on our calculations by comparison to the value we were given at the beginning of the equation. So this answer is an acceptable value for the equilibrium concentration of HF and the equilibrium concentrations of H2 and F2. And with that, I'm going to go ahead and close the video.